Completing the square. So first we need to talk about perfect squares. So a perfect square is a quadratic expression that is written in this form here. So a plus b all squared or a minus b all squared. So for example, x plus 2 all squared is a perfect square, 2x minus 3 all squared, 7 minus 3x all squared, etc. They're all perfect squares. So when we look at perfect squares, if we expand out a perfect square, we get the following expansion. And you'll see you can do that quickly yourself. If you have a plus b times a plus b, you're going to get a times a, which is a squared, a times b, which is ab, b times a, which is ab, and b times b, which is b squared. And so we get a squared plus 2 lots of ab plus b squared. So what's important here is being able to identify this pattern, and this can be useful in expanding these kinds of expressions very quickly. It can also be useful in factorising. If you can see these patterns, then you should be able to factorise back straight away. So in this first example here, we have x squared at one end and 9, which is 3 squared at the other end, and then plus 3 squared at the other end. So in order for this to be a perfect square, that middle term would have to be 2 times x times 3, which in this case it is 6x. The fact that it's negative 6x, sorry, I won't. So we've got negative 2 times 3 times x. So the fact that it's negative just means that when we factorise, this is going to be x minus 3. All squared. Looking at the second example, the first term here is 3x all squared, and the last term is 2 squared. So what we need is for the middle term to be 2 times 2 times 3x, which is 4 times 3x, which is 12x, which is correct. So this is therefore a perfect square, so it will be 3x plus 2 all squared. So the operation in the perfect square bracket comes from this operation here. So the coefficient of x, whether it's positive or negative, will tell you about whether you have plus or minus in the bracket. Okay, so that's a little bit about what perfect squares look like and the patterns that we get in expanding them. So what we want to get towards is this idea of completing the square, and basically the main reason you might complete the square would be to get a quadratic equation from general form into turning point form, and that can be a really useful thing to do for a number of different reasons in terms of graphing, finding inverse functions, all sorts of different things. So we'll come back to uses to it down the track. But for now we just want to deal with the algebra of this process. So the next thing we need to realise is that what we're trying to do in this process is to create perfect squares. So again, we need to be clear of the patterns that go on in a perfect square. And one of the things, a couple of the useful things that we need to be able to see are that the relationships between what goes on. So this middle term here, if we halve and square it, we will get the end term. And that's important. That's one of the key things about completing the square. The other thing that's important to realise is that when you come to then factorising, the term in the bracket will be half of the coefficient of x squared. So this coefficient of x squared is key. If we know about that, we can work out what we need to add in and take away to create this perfect square. So having a look at these couple of things, if we've got x squared minus 12x, what number would have to be on the end there for that to be a perfect square? So obviously to get from the coefficient of x to the constant term at the end, we halve and square. So half of negative 12 is negative 6, squaring negative 6 is positive 36. So we would need to add 36 onto the end here to make this a perfect square. And when we do that, this will now be x, and we're looking for half of the coefficient of x, so minus 6 all squared. Looking at the next example, x squared plus 2x, so we want to halve and square, so we'll have x squared plus 2x, half of 2 is 1, and 1 squared is 1. So plus 2x plus 1, that's a perfect square, and it is equal to x plus 1 all squared. Remembering that this term in the bracket is half of the coefficient of x. Alright, so what number must we add to x squared plus x to produce a perfect square? Okay, so we've got x squared plus x, so it's 1x, so we need to halve and square 1. So half of 1 is 1/2, and 1/2 squared is 1/4. And when we do that, we've now created a perfect square. It is x plus 1/2 all squared. What number must we add to x squared minus 3x to produce a perfect square? So we've got x squared minus 3x. We wish to halve and square the negative 3. So that's going to give us half of negative 3 is negative 3 on 2. And when we square that, we'll get 9 on 4. And this is going to be equal to x minus 3 on 2 all squared. So this idea of how do we create the perfect square, given the first two terms, is what's important in completing the square. Okay, so let's have a look at actually going on to complete the square now. So here we have x squared plus 6x plus 8. So x squared plus 6x. Now it's not a perfect square, because I know that for it to be a perfect square, half of 6 is 3 and 3 squared is 9. I need to have 9 on the end here. So we're going to create the perfect square. I'm just going to leave the plus 8 sitting over there. There are different ways you can write this down. I always do it this way. So I want to create the perfect square, so I know it's going to need to have a 9 on the end for it to be a perfect square. Now I can't just add 9 into an expression just because I feel like it, so I'm going to need to take away 9 as well. So we actually haven't changed anything, but we've rewritten it in a way where now here we have a perfect square. So we can factorise that. That is x plus 3 all squared. And then outside of that perfect square we have minus 9 and plus 8, so minus 1. So we've completed the square. Let's have a look at another example. So we've got x squared plus 3x. I need to work out what to add on to make it a perfect square, and then I'll have to take that away as well. And then I've got minus 5. Okay, so we wish to have half of 3 and then square it. So this is x squared plus 3x plus 9 on 4 minus 9 on 4 minus 5. And this here is my perfect square, which is going to be x plus, now remember the term in the bracket is half of the coefficient of x, so 3 on 2 all squared. And then outside of that perfect square I've got minus 9 on 4 minus 5, so I'm going to need a common denominator there. Minus 9 on 4 minus 20 on 4. So we're going to have x plus 3 on 2 all squared minus 29 on 4. And we've completed the square. So if your coefficient of x is an odd number, you're going to have fractions involved in this, so you just need to deal with that. It's obviously much nicer and much easier if the coefficient of x is an even number. Okay, a couple more examples here. These ones are slightly different because these are non-monic quadratics. Now, you cannot complete the square for a non-monic quadratic. So the first thing you have to do, whether it creates fractions or not, is to factor out that coefficient of x squared. So we must factor out a 2. So we've just got a monic quadratic. So we'll have x squared plus 2x, and it's going to create a fraction at the end here, but we just have to deal with that. Okay, so now I'm going to complete the square inside the bracket. What you need to be careful about here is that you don't lose that 2 out the front. There's nowhere for it to go, so make sure you don't lose it, and be extra careful about brackets here. We'll end up with quite a lot of brackets along the way, so just don't lose track of what's going on. Okay, so I now want to complete the square inside here, so I've got x squared plus 2x. I need to think about what I have to add on here to make it a perfect square, and then I'll take it away as well. And then I've got plus 9 on 2. Okay, so adding in here, so half of 2 is 1 and 1 squared is 1. So we need to add in a 1 to make it a perfect square, and then we'll take away the 1. And here we have our perfect square. So we've got 2, and then we've got x plus 1 all squared. Outside of that we've got minus 1 and plus 9 on 2. Okay, so we've got 2 times x plus 1. Now this is where you might have lost a bracket in this bit here, so please be careful about that, because you'll end up not multiplying your whole thing by 2 at the end properly. Okay, so we've got x plus 1 all squared, then we've got minus 1 plus 9 on 2. So minus 1 is minus 2 on 2. So negative 2 on 2 plus 9 on 2 gives us plus 7 on 2. Okay, now we want to put our 2 back in. So we're going to expand out this bracket. So we're going to have 2 times x plus 1 all squared. And we're going to have 2 times 7 on 2, which leaves us with 7. Okay, let's just have a look at one more example. So again, it's non-monic, so we must factor out that coefficient of x squared. So I'm going to take out negative 2. I'm going to be left with x squared plus 1 half x and minus 21 on 2. So we've got some fractions going on here. Okay, so we're going to have x squared plus 1 half x. Figure out what to add and subtract. Minus 21 on 2. Okay, so we have to halve half and then square it. So half of a half is a quarter. So that's going to make our perfect square. So we've got negative 2 x squared plus half x plus 1/16 minus 1/16 minus 21 on 2. There's the perfect square. So it is x plus a quarter all squared. And then we need a common denominator here. So we've got minus 1/16 minus 21 on 2. So we want to make a common denominator of 16. So I'm going to multiply the top and the bottom here by 8. So 21 times 8. Well, so 20 times 8 is 160. And 1 times 8 is 8. So it's 168 on 16. So negative 2 x plus a quarter all squared minus 1/16 minus 168 sixteenths, so it's minus 169 sixteenths. And lastly, I want to expand back out with that negative 2. So negative 2 times the bracket and negative 2 times that fraction at the end. So negative 2 x plus 1/4 squared plus, because we're multiplying by negative 2, 169 on 8. And so there's a little summary of completing the square. As I said, I would never use completing the square to solve an equation. It is a valid method because once you've completed the square, now you can solve these equations by rearranging. But if I couldn't factorise, I would use the quadratic formula. Where completing the square does come in usefully is in sketching quadratic graphs, creating turning point form, finding inverse functions of quadratics, dealing with the equations of circles in expanded form. So there are lots of times where you'll need to use completing the square, but I would say that it's not a good method to use if you're trying to solve a quadratic. You would just use the quadratic formula, which we'll talk about in the next video.